Alright, and so welcome back to section 1.6. I know we're still on section 1.6. It's a long section. The section is called Other Types of Equations, and we're working through some other things that can come up, like radicals, problems with fractions, a lot of things where you have to check your answer and make sure they work back in the original problem. The last type of problem is this idea of substitution that sometimes helps us solve a difficult problem by breaking it down with a substituted value. The example I have here is 3 times a quantity, 7x plus 32, minus 7 times a quantity, repeated quantity, 7x plus 32. And I could have kept on using 7x plus 32 as a quantity, repeated quantity, and it just wouldn't make sense to keep writing down 7x plus 32 if I see it's the same one repeated many times. So oftentimes when we see a repeated value, we'll substitute it as x equals that, and then we'll just simply say, hey, I'm going to let this thing here stand in as just a regular x. Call that x, and then that's the same thing, so that's also x, and I can write a simpler equation, 3x, that being x, minus 7, that being the same thing, x equals that 48, and then solve it simpler without that repeated quantity. Now normally we do it as a u. That's because u is not a commonly used variable in algebra, I suppose, so it's kind of hanging out there, you know, not normally in the typical equations we see. So it's kind of nice to substitute with a variable that's not already used in the equation. So you'll see the u substitution used, but really it could be any letter, any symbol. You could call it star or whatever you felt like. So you could make a symbol there. That's all that the variable is doing, is standing in the place of that as a symbol. So anyway, I used x just because that's normally what we're so used to using, but you will see u in the book normally. So 3x minus 7x equals 48 can be solved with our reverse operation, solving linears, and get a solution of x is negative 12. Now what you need to remember though, if you've used this substitution method, you've not really got the final answer. You've got the substituted answer, the easier route that you use, but it's not done because you've got to say, oh, you know, this was our pretend x. It wasn't really in the original equation like that. So now I've got to say x is really 7x plus 32 that equals negative 12. So I change x into its real value that I substituted in earlier, sub that because those are equivalent. X is 7x plus 32 in our setup. So I sub it back into its real value equal to negative 12. Then I solve that equation, giving me the real solution. This should work, negative 44/7 when I plug it back in for the original equation. It subs back in to be accurate. So that's the concept of all of these, and we're going to work through some different examples and see how that looks in different ones. All right, so I am on page 143. Page 143, where it says equations quadratic in form. So this is a lot of times used to help us solve more complicated equations, and we'll see this on example 8. So the example I showed you was a linear, and we probably wouldn't even make the effort to substitute on a linear because they're just not as hard to solve anyway, but it still works. It's still an idea of substituting in something easier to get your work done and then unsubbing that difficult part at the end. So what we see repeated on this one is x plus 1 and x plus 1, which I would say that's repeated. It's not a bad repeat, but you know, we could just call that regular x, and then remember at the end to go back and change it back into x plus 1, its real value. But this one also has an additional complication. It's not just to the first and the second power like a normal quadratic. It's to the 1/3 power and the 2/3 power. So that complicates it. I would like to call this whole block, and it's usually the middle term if it's in an organized form, so, but it could be out of order, but normally they flow the biggest, the square, what would be the square term, the middle term, the constant, and it's a quadratic in form. If I let all of this be another symbol, like I said, the book likes the letter U normally, but it could be any symbol. If I called this whole block U, and I were to square this block squared, you'd multiply the exponents and 1/3 times 2 is 2/3. So if this is substituted as the u value, the middle term, then this will be the square of that, u squared. So it is quadratic in its form. Now I recommend that you make a note that we're letting u equal all that middle stuff, or you can just circle it and write over top of it. But do remember that is going to have to be changed back at the end to get the real final answer. So we're pretending this is just a u to make my work easier, which makes this u squared. So this would be the square of that, u squared. It's got to subtract u and then a minus 2. And now we have our substituted quadratic equation. And then it's easier in this form to think about factoring it or using the quadratic formula to get your two quadratic solutions. In this case would be 2 and -1. So again, remember, those aren't your final answers, they're your substituted ones. So you still got to go back now and fix it. So u is really, in our map key right here, we let u stand in for whatever you circled there. If you wrote it down below, this is what it needs to be changed over to. Under where you had u equals 2 and u equals -1, the two solutions, change u into its real value. X plus 1 to the 1/3 equals 2. And here, x plus 1 to the 1/3, that's what u really stood in for, equals -1. And then we solve those resulting equations to get to our final answer. Okay, so we learned this earlier in the section. If something's to the 1/3 power, if we take it to the reciprocal, which would be 3/1 or 3, that will take care of that. So we take each side to the 3rd or 3/1 power. It cancels out that exponent, brings out the x plus 1. 2 to the 3rd can be calculated as 8. Subtract the 1. 8 minus 1 is 7. So that's one of our real solutions. Doing this side, take this side to the 3rd power, this side to the 3rd power. That gets rid of that 1/3, brings down the x plus 1. -1 raised to the 3rd, and again you can check that on your calculator, but it's -1. Subtract the 1. -1 minus 1 is -2. So there are our final actual answers that should work. When sub back in the original problem, that's what we should always make sure we're aiming for, checking it. Alright, so there's one type like that. So let me show you another. That's the concept though for all of these. You look for something to substitute and then you unsubstitute at the end. So here's another type of that useful for substitution. You'll see example B. The negative exponent makes it more complicated. So we don't want to try to be factoring or using the quadratic formula. You actually can't use the quadratic formula unless it's in real standard quadratic form. So, well, it's got the negatives in it. But anyway, I wouldn't try to work with the negative exponents. I would substitute it out. So what I don't have a parenthesis of repeated values, but I have this x to the -1. I'm going to call that u. If I were to square that term, and you'll notice this is true for this little section of these contrived problems, but do notice that it really does work. If you were to square this term, you'd multiply the exponents. -1 times 2 would be exactly what you have over here. So if I let this be u, if this is squared, it would be this term here. So it'll make it quadratic. It'll make that u squared, u equals 2. So I do make a note that I'm letting u stand in for the x to the -1. Then I rewrite it. This is u squared. This is what I let be u equals 2. So now I've got a true quadratic, and once I have it in the quadratic form, you can use the formula. Once it's in standard form, you could use the formula on that, or I'm going to factor it though. So I would take some time, think about how I could combo this to work. I think that'll do it. 3u plus 2, 2u minus 1. Set each parenthesis equal to 0. And then solving each part, we get two substituted solutions. So you want to go back in and find the real answers though by unsubbing. So we take what u represented in the original problem, x to the negative 1, or you made a note of it here, but underneath where u is, we no longer call it u, we'll go back to what it really is. X to the negative 1 equals negative 2/3. And over here, x to the negative 1 equals 1/2. Then we solve for the real x. So to get rid of the negative 1, if I take negative 1 to the negative 1, you multiply inner and outer exponent, so negative 1 times negative 1 makes x to the positive 1, or regular x. So do the same thing on this side. Note when you take negative 2/3 to the negative 1, which check it on your calculator, but it's going to flip the answer. The negative exponent will always flip the fraction to its reciprocal. It's still a negative number, but it reciprocals it. Okay, same thing here. Negative 1 power each side will flip 1/2, becomes 2 or 2/1. And then those are our final answers for that. All right, we're going to do that one more time. One more type problem that's kind of as common to show up. There would be infinite ways they could throw this at us, different reiterations of this concept. But I'm going to show you example 9, the last one that's kind of common to your exercises that you'll see in the book. All right, example 9. So here we have, again, not a true quadratic the way it is, but it's quadratic in form. If we could substitute it out in some way, we could rewrite it as a quadratic. So x to the second, if it were squared, this part only, I don't have any common numbers or repeated things, like we did on the first example, just the x part is squared. If you squared that, that would be x to the 4th. So this is the square of that. So if I pretended this part was my u, this part would be u squared. So then it would be a quadratic. 12 u squared minus 11u plus 2 equals 0. But again, always make a note what you're letting u stand for, which is the x squared part, to make this work out for us. So once you have your substituted equation, which these turn out to be quadratics, then you can use your formula or factoring. Let's see if this works. Yeah, that would factor and work for me, setting each part equal to 0. You get two solutions of 2/3 and 1/4. So again, don't stop there. You never want to stop with the u solutions because those aren't finished, finalized. You've got to substitute what u really is in your key up here. So u should be x squared equals 2/3. And this u should be subbed back into its original value, x squared. And then we have to solve those resulting equations. So to solve x squared equals 2/3, we square root, right? Square and square root go together, and that reduces to the x. But don't forget, when you take the square root of both sides, we learned this in section 1.4, you have to say plus and minus of your solutions. There's two solutions when you have to square root to solve. So square root of that. And we're going to talk about cleaning that up a little bit. The same thing on this side, square root, square root. This one's perfect. 1/4 is a perfect square, so it cleans up nicely. You might notice 1/4, if you square root, the top is square root of 1 is 1, the square root of the 4 is 2. So that'll come out of the radical perfectly as 1/2. Plus and minus 1/2. Those are nice. But this one over here that still has a radical around it, you're never supposed to leave a radical around a denominator, so we do need to clean it up a bit. So we would rationalize the denominator by breaking the fraction into top and bottom radicals. And then to make the radical in the bottom perfect, we'll times it by a match, square root of 3. We always have to do the same thing to top and bottom, keeping the balance just like we do on equations. We also balance top and bottom of fractions. Square root of 3 times square root of 3 brings out a regular 3. And square root of 2 times square root of 3 is square root of 6. So that's how it's preferred to look. Square root of 6 over 3 would be the right form for that. Notice now we have a total of 4 solutions. It's a 4th degree equation, so we should be looking for 4 answers for 4th degree. The degree determines how many solutions you have. So we have a plus and a minus, radical 6 over 3, that's 2 there, and a plus and a minus 1/2, which are rational solutions over here, so a total of 4 answers. If you're thinking this is kind of a tough section, I think so too. I think it gets easier after we get through 1.6 and 1.7, so hang in there. I think these are tough sections too, just tedious, long problems. So please review these examples and hope this helps.